This probably won't take us that. It'll probably take maybe 25 minutes or so to get through. So, guys, please. And what I want to look at today is how do we set up these things to make those problems work. And it all stems from the idea of working with inverses and having the properties of inverses and stuff. So. Remember when you're solving for inverses? Yes? There's a couple more on there. So when you're working with inverses, you have this. If I start with that regular old boring function, and I want to find its inverse, what did you guys do? Yep, you flip-flop x and y and you resolve it. So what we did was, then we would resolve the function. We would resolve it and say that x plus 3 all over 2 equals y. And in doing so, we then would say that we could say that and verify that those two functions were inverses of one another by substituting in one for the other. That was when we did function notation, f of x, and things like that, and whatnots. Well, what we would say is that to verify that these two were inverses, it was 2x minus 3, and g of x was x plus 3 over 2. You'd put in one for the other. So you'd say 2 times the quantity x minus 3 over 2. Minus 3. Well, this drops out. You get x plus 3 minus 3, and that equals x. And you do the same thing going the other way. 2x minus 3 plus 3 all over 2. Well, that becomes 0. That drops, and that all equals x. And then we would say, since both values simplify out to equal x, that therefore they were inverses of one another. That's a big thing. Also, yes, sir?
The intersections of those, like those two lines, the intersection would be 3, 2.
I don't remember what that, but yeah. But also, what happens when you're doing inverses, if you look at them graphically, 2x minus 3, and the other one was x plus 3. Remember, if you look at it graphically, there's always, gentlemen, stop. Please. Thank you. If you look at everything graphically, no matter what, your two graphs that you're looking at, your two functions, there's always this imaginary line, y equals x, that shows that each point on either graph are equidistant to that line y equals x. That's how you verify things out being inverses. And whatever their intersection, they may or may not have intersection, and so on. So what happens here is that when we've been talking about what's called logarithmic form and exponential form, those two are inverses of themselves. Let me show you. When we did this log form, we said that log base b of y equaled x. And we said that exponential form was b to the x equals y. We can say that those two functions are inverses of one another by literally substituting back and forth. Here's what happens. If I say that log base b of b to the x, that looks eerily similar to what we had done earlier. If you go back to that first set of problems from yesterday, we talked about simplifying logarithms. We had the two basic ones, log base b of b equaled 1, and log base b of 1 equaled 0. Yes, Kate?
Are we going to go with the ones where it has like the number before the log?
Yeah, I'm getting there. That's where this is going to come into play, of why you can do certain things. And it'll be in about 2 minutes. All right. So what happens here is that logarithms all have a base. exponential functions also all have a base. In this case here, my logarithm has a base b. My exponent part of it also has a also has a base b. Are those two the same? When those two base parts are the same, whatever is up here, false. They undo one another. Log base b of b to something undoes it. So you had a problem yesterday where it might have been log base 3 of 3 to the x. Base of 3, log base 3, the exponent part also has a base of 3. They undo one another via inverse properties, and you get x. The reason is log base b of b is 1. Okay? It undoes itself. That's where this comes out of. Excuse me. Here you go, sir. Maybe. If you'd like one. Yes, ma'am.
So we didn't have to do the other ones?
That's what I had been saying for a while because you didn't know how to do them.
Yeah.
Goes through the other way, and like you were asking Hopworth about what happens when the number's out in front of it. Well, if I look at the other form and I take the log base and I substitute in here for x, because that's what x is, if I say it's b to the log base b of y, again, notice how the exponent has a base of b. The exponent itself is a logarithm. It also has a base of b. They're the same bases. What drops? The y. Okay, so what happens there is that they undo one another. So that example, that very first problem where it was 5 to the log base 5 of x, this 5 is a base. The logarithm has a base of 5. They're the same, which means they undo one another, and your answer would have been just plain old x. That's how that works. What's that? That's how these problems are going to work themselves through. Because what you're going to be able to do here is work with logarithms and exponents and rewrite values to have common bases. And that's where knowing 8 is 2 cubed, or 64 is 2 to the 6th. Yeah?
So would your answer just be x?
For this one? Yes. Because it undoes it. There's a lot of little things here, and I'm going to have a ton of examples today, and it'll be like, oh, that's all it was. Sir?
All right, so for like, say example we had number 52.
Will you read it to me, please?
It's log 4, 16x.
Okay, and that's what this is something that I was getting to in a second. What you want to do, bless you, to be able to simplify this out, is that in your mind you have to think the only thing that you know how to do right now is work with common bases. You want to get common bases. How do you rewrite 16 as a base 4? 2 squared, right? So what you do is you rewrite this as log base 4 of 4 to 2x. The answer is 2x. Very good. You're rewriting to a common base to undo itself. Because exponential because the rule is going to be in right over here, is you're going to have 2 of these. That's how they undo one another. If you get these to be common bases, they undo it. If these 2 bases are the same, they undo it. So sometimes you're changing the base of the exponent. Sometimes you're changing the base up front to do something. This comes more and more into play as we go to solve equations. Now, the other day I showed you guys that you had, how do you get 2 to the x equaling 6? Yes, ma'am.
No, I have a different question.
What do you got?
What do you do if there's no base for the log?
I'm going to explain that in a second. All right? Let me ask you this real quick. What's the coefficient? Okay. Logs have a rule, and again, I got ahead of myself by looking at the assignment before realizing it was a half day. It'll take me 2 seconds to explain it. There's what we call a common log, right? Now, if you think about the rules here, I would have to do something to both sides of an equation to keep it as a valid statement to allow this exponent to fall. So what happens is that you'd have to do log base on both sides. What I mean is, if I do and write this as a log base 2 of 2 to the x, I created a log base on one side, I'd have to do a log base 2 of 6 on the other side. These two bases are the same, which undoes all the exponent stuff and allows the exponent to fall, and that tells you what the answer of x is. That's how you get your decimal values and things like that. That's how this stuff works. Logarithms are there to work for x, to solve for x as an exponent. That's why we use them. Okay? That's how they undo one another. Okay? Now, what you're asking there is what's called a common logarithm. Common log is just plain old log. Plain old boring log means log base 10. That's all that means. The button on your calculator is log, that says log. That's common log. That's log base 10. That was the way that everything started out as a base 10. And then there's actually ways to calculate different bases by using base 10. And back in my day, we had to use tables and stuff to do all this, to figure out exponents. But now, on your calculators, you can change bases all day long and not have to do it. If you hit alpha window 5,
Like one of my friends showed me this one.
yeah, and it'll automatically, you can change your bases. Like I said, back in my day, we had to actually know how to switch and do what's called change base formulas.
So are we gonna have a calculator on this test? Or?
To solve equations, you're gonna need a calculator. I can give you tables.
No, no
That's tables.
Thank you, you can stay. So what happens is that you get this, what's called, anytime you just see plain old boring log, it's base 10. So if you had to figure out and simplify this, log of 100, you'd want to rewrite 100 as a base 10. So 100 as base 10 is what?
2.
Well, 10 squared, and your answer is 2. So that's what that meant. What they do here is that they don't write the 10 there. It's kind of like when I ask what's in front that you don't see. It's the same idea. It's the math etiquette of not writing it. It's like you're being hoity-toity. Okay. Now the other one that becomes a little bit weird. Actually, let me go do another example before we get too far. Let's try these two. Log base 2 of 64, I'm going to simplify that. In order to simplify that, we need to do a base change. So if I want to do a base change, I want to sit there and think about, okay, in order to get rid of the logarithm, I need to figure out a way to rewrite 64 as a base 2. 2 to what power is 64? 2 to the 4th, well, 2 squared, and then 2 to the 4th would be, what, 16? 5 is 32. 6, we'll get there eventually. So this is the log base 2 of 2 to the 6th. So your answer is 6. Because the two bases are the same. The two bases are the same, they kind of undo one another, and it allows the exponent to drop. What's wrong, Hoppenworth?
Nothing. I just have a
You had a revelation? Nice. How do I rewrite 5 as a base 25?
Or no, 1 5.
How do you rewrite 5 as a base 25? What is it? No. If I did 5 to the negative 1/5, that means it's 1 over 5 to the 5th power. Big number. Yup. Negative 1. All right. So if it's 5 to the negative 1/2, that means it's 1 over 5 to the 1/2.
5 to the second.
You need to turn a 5 into a 25. If I square the 25, if I square the 5, right? But how do I make the 5 look like a 25? Yes.
Just change it to a 25.
What's 1/2 power mean? Square root. So 5 is the square root of 25. So yeah, there will be some of those root ones that'll come back and kind of trick on you. You could take it longer than that. Okay. So yeah, you will see stuff like that. You have to sit there and think, okay, how do I rewrite that? And go from there. Okay. Yeah, the answer here would be a half. Okay.
So we weren't wrong when we said this change.
You were on the right track, but you had to think of. Yes, you were on the right track for that. What's that? Caught it. I didn't drop it. I can't put a tick mark on it. I caught it. So log base 6 of 1. Very good.
What?
Oh, yeah.
What's anything to the 0 power?
I get that part. I'm just confused. Like, I don't know how to explain it. But like, why instead of 1 doing? I don't know.
Should we change the top number beginning as the bottom?
Pretty much. Now look at this one. You have 10 to the log of 4. What's the base of the log that you don't see? 10. Are those two bases the same?
Yeah.
What's your answer?
4.
What? Oh yeah, the log on it.
Are the bases the same? The exponent drops. Common base is base 10. So if you just see plain old boring log, this is base 10. Okay. What's that? Okay. Let's look at another one. Hey, look at this, a whole thing about common log. Anyway, but we have to talk about what's natural log. So, we come back, we've already talked about common log. Common log's not a big deal. Natural log is the goofball. Natural log is when you have log base E. LeBlanc, you're going to be surprised. It's okay. Here's what happens. They use, guys, if you look on your calculator, you will see e to the x and ln of x, I believe, are on the same button. I think. Yes, ma'am.
How do you put it with the subscript though?
I will show you.
LN below.
Okay. Now, they use ln because back in the day there was this thing called Latin, and it was pronounced out as log of the natural, otherwise known as wonderbat.
This is like the 99% one.
Wonderbat. Simpsons, Homer at the bat. It was his bat. So here's why we have natural logs. Yeah, absolutely. Let me show you why we use natural logs. We use natural logs for inverse stuff. Let me get the right button. When we're using inverses, we have to be able to use natural log with inverses. And the inverse of a natural log is e. E's and natural logs undo one another because natural log is log base e. So I have to show you guys a term and how things work to undo certain things. So let's take this y equals the natural log of the quantity x minus 1. And then we're going to do and work through to find its inverse. Okay. Now, when we find inverses, yeah, Jane.
So natural log is just ln to x, or is it like? I'm confused.
Natural log is log base e.
Okay.
Okay.
Is this a problem or an equation?
I'm doing an inverse. Okay. So if I'm going to do an inverse here, the first thing we have to do is just flip flop x and y again. Now, what I want you to remember is that natural log is log base e. So in the back of your mind, this is the same thing as writing this out. It's the exact same thing. They mean the same, but it's cutting your workload in half.
So ln and log are the same.
Yeah, log base e and natural log are the same. So what happens is, you need to be able to undo a natural log. Well, to undo a natural log, you're going to go back and remember, natural log is log base e. So to undo a log base, you do what's called exponentiate. I don't know if that's a real word, but it sounds good. What I mean by that is, I'm going to write this out long form again. So we said that this is log base e of y minus 1. If I rewrite this as e to the log base e of y minus 1, I have to exponentiate both sides. Basically what I'm doing is I'm taking my starting part of the equation and I'm turning the whole thing into an exponent. So I'm exponentiating it. I don't think it's a word, but it makes a lot of sense. Okay? Good chance. So now, notice on the right-hand side, e to the log base e, it undoes itself. E undoes natural logs. So what drops? The y minus 1. So then I get e to the x equals y minus 1. Therefore, e to the x minus 1 is y. Oh, thank you.
It is a word.
It
Yeah, I
is?
just looked it up.
It is?
Yeah.
Is that what it means?
It's a word.
How to raise something to an exponent?
The mathematical operation of raising a quantity to a power. Also called integration.
What's it called?
Is that kind of sadder though, because then that means you didn't like really create any word.
No, but in my mind I always thought I was. Don't bring me down, Hoppenworth!
What's it called?
Exponentiate.
Is those the answers?
So again, to show that these two are inverses of one another, if they both wind up equaling the same out, if I take the natural log of, what is it, e to the x minus 1, or sorry, plus 1 minus 1, what happens here if I simplify this out by substituting back in, I get the natural log of e to the x. Natural log is log base e of e to the x, which gives me x.
Wait, is this
Why
the
did
same
you do
word?
that?
Oh,
I'm going back to that whole idea of,
Okay.
I'm going back to real quick to show if you have two functions,
Like,
Oh.
it's cool the fact that I showed
if you put them in for each other,
for once.
That is cool.
If that happens, they're inverses. I'm just showing that I can put one in for each other and it just equals x. Okay? Also, yes ma'am?
Why are you able to drop the E log?
This part here?
Yeah.
Okay. Base raised to a log of the same base. If these two bases are the same, the rule is the exponent falls. It doesn't matter what it is. It just is base e. E is just a crappy decimal. So, crappy decimal to the log base of the same crappy decimal, the exponent just falls then. That's it. Now, if you look at it graphically, let me show you how to put this in the calculator. Yes, ma'am?
No, wait 1 minute. If you find the inverse, like, can you only use that when it has the ln?
For e, no. You can do inverses by exponentiating whether it's logarithm with any log base, because if it's log base, if this was log base 6, I'd put a 6 there to both sides to be 6 to the x. It would work the same.
If y equals log base 9
Yeah.
x,
You 9 it.
it's like a
That's all it is. Now, if I go to the calculator real quick, and I put this in, if I put in e to the x plus 1 and natural log of x minus 1, let me show you how to type that in. So e to the x, so e, it's right here. E to the x, and then it was plus 1, sorry. The next one was natural log of x minus 1, I believe. If I look at the graph of those two, you'll see how they are inverses of one another as they go through. What it doesn't show here on the red line is that this does fall. It does continuously fall.
well, why does it stop there?
The calculator resolution, that's all. It just depends on how big it's set. It approaches an asymptote. Okay. Now let me show you another one. Excuse me. I want to find the inverse again. I'm going to find the inverse of this one. Is that so? Why not? Yeah, it's not base 749x. No, it's, yeah, they're all, that's all there. So I'm going to do the inverse again. First step of finding inverse is to flip-flop your x and y. We okay with that? Next step is to then see if I can simplify my log. Well, 49 is, how do I rewrite that as a base 7, or can I? It's 7 squared. Because, no, 7 squared, because what's 49? 49 is 7 squared. If it was 7 to the half, it would be the square root of 7. Yeah. So this is the same as y, or log of 7 to the 7 2y. Now what happens? Math. Yes. So I get x equals 2y, which means y is x over 2. 1/2 x or y or x over 2. There's the inverse.
Give me a second to work.
And then you check them by putting them in the graph?
You can check it by putting it in the graph, because if you go back to the original problem, isn't this the same as saying log base 7 of 7 squared, or 2x? So y equals 2x. That's the first equation. There's its inverse. So those are inverses of one another. It just so happened to be a hidden logarithm thrown into it. That's it. Okay? As you start going through.
So really, x just equal y.
What's that?
Doesn't x just equal y? That because it's like 2y would equal 2x. If you work it back here.
If you put it in for one another, if you say that y, if I do this where y equals 2x, I'm sorry, 2 times x over 2, that equals x. And if I go the other direction where I say y equals 2x over 2, Well, that also equals x. That verifies that the two of them substitute back and forth, they both equal x, therefore it's an inverse, they have an inverse relation. Alright? Let me see if I can find another one of those you can exponentiate. It's fun. Okay? That's just y equals, sorry, we cut off a little bit. So this is y equals log base 1/2 of x. And I'm again going to go ahead and find the inverse. So when you go to find the inverse, after you write it out, the first thing you're going to do is what? Yep. Flip-flop x and y, just like we have. Excuse me. Now, Fleming, this is where you were getting at. What do I have to do to both sides to get rid of that log base 1/2? Exponentiate it with a base of 1/2. Yep, that's all it is. You exponentiate it as a 1/2 base, which tells me then that it is 1/2 to the x is y. I exponentiated it. It just so happens in this case the base of the logarithm is a fraction, which is fine. And there's a reason we can do fractional bases for logarithms, and it's going to help us next week when we graph them. Actually, graphing logarithms, remember how we graphed e values where you only had to get the intercept and an asymptote? Yes. But when you graph logarithms, all you're going to graph is that property on the right. Log base b of b is 1 and log base b of 1 is 0. You're going to pick values of x to generate the 1 and generate the 0. And then it's just a matter of knowing what direction it moves. That's it. Okay? One more, or you want to try one more? Yeah. I'm going to say logarithm stuff. Does that sound like a deal?
Yep.
Good. One more inverse. One more inverse, please. Remember, you can rewrite f of x as y equals. Perfectly fine.
Okay, you press second raw, and you scroll until it says end. Raw.
Yeah, just find the inverse. Yep. I don't know. What's your first rule?
I want to get better.
No base is 10, so rewrite x equals log base 10 of 3y plus 2. So I have to exponentiate it by putting what? 10. So 10 to the x is all that. So 10 to the x minus 2 divided by 3 is y. If you substitute that back into the original, excuse me. If you substitute back and forth, then you're going to have the log base 10 to the x minus 2 plus 2 over, what was it? Divided by 3, and this was times 3, I believe. So these drop. Those go away. Log base 10 of 10 to the x is x. It's a tricky little thing to start working through, but you're going to want to just continually try to work through your bases. And remember, when you exponentiate, that's how you use same base to both sides to get things to drop. Log base b of that drops and goes from there. Now, what I have for you then tonight then are the 8 problems that I thought we taught you yesterday, but I didn't. And then the next 12, I think. What is it? Is it 4864?
Yeah.
So all of it would be 48 to 64.
Where's the 55?
It's supposed to be the 55 was the one that I like I explained earlier. Yeah. So the 48 to 55 is included now.
But we already did.
But you did. Yeah, just put them all together on the one sheet, then we'll collect that on Monday. And then on Monday we'll do graphing. Graphing for logarithms should only take about 20 minutes or so. And then we'll get started on that. Tuesday we will do log properties about what's called expansion and condensing logarithms. We need to know how to do that in order to solve logarithm equations, which will probably start Thursday, maybe a bit of Monday. We will not be able to test next week like I had thought. Not the end of the world. It'll probably be the middle of the following week. Okay?
Yep.
Fine.
What's wrong with you, LeBlanc?
Connor Marcus is gonna be so sad in chemistry.
That's what my kids say in movies, watching Little Rascals.
I bought one